Welcome to Orgoland in cyberspace. This is the very first lecture of the remaining part of our Chem 211 semester, and we're going to start naming them by lecture number, similar to what we have done in the past. This is lecture 19A, and we're going to do a quick review of what we covered in lectures 16 through 18. That was on SN2 chemistry, because our overall goal is to learn about organic reactions. And that's the best part of the remaining part of the semester. I can't wait to show them all to you. So no matter what Calvin and Hobbes says over here, I don't really think we need to be organic chemistry atheists. We can actually believe, and I'm going to show you why. Okay, so let's see what happens. For a quick review, specifically SN2 is what we covered in lectures 16 through 18. I want to talk about how there were those 4 factors that we need to keep an eye on. The very first one here is nucleophilic substitution. Excuse me, the very first one is the nucleophile. And let's make sure we're clear about it. It must be good. It's got to be a good nucleophile, and that means it's got to be charged. So charged nucleophiles like OH- are really good nucleophiles for SN2 reactions. The second thing that every nucleophilic substitution reaction needs is a substrate or an electrophile. And this is really important in an SN2, that we have to try to keep them as unbulky, as sterically unhindered as possible. So primary would be good. Then secondary and tertiaries, let's just put a big old cross through here that no reaction ever really occurs for a tertiary. They just hate to react in SN2 reactions. And keep in mind about the benzylics and allylics and aliphatics. Those are the last names to our substrate. So every time you look at a reaction, you're going to want to call it by its first name for the substrate. Is it a primary, secondary, or tertiary? And its last name, benzylic, allylic, or aliphatic. And you need both of these to have a really good SN2 reaction. They both matter in the rate law for SN2. We'll be looking at leaving groups in the next lecture. But in 16 through 18, we started looking at the solvent and its importance. And notice it's fourth. It's very unimportant. But sometimes if everything else is tied, you can't determine what mechanism is going on. Sometimes we will look at the solvent as the last resort. We'll look at the solvent. And in our SN2 reactions, we saw that we wanted an aprotic solvent is best. Okay? But isn't always necessary. So you can see from the reaction that I've given as an example above, I don't have an aprotic solvent. This is a protic solvent. And please go back and check out lectures 16 through 18 to get those definitions clear in your head as to what they mean. But why would I use a protic solvent in this SN2 reaction? Well, it really is because the solvent has one overall goal that we really have to have at play in this game. This game of nucleophilic substitution, its goal is to dissolve the reactants. And so notice in our reaction example above, I have OH-. And OH- is a great nucleophile. It usually comes in the form of potassium hydroxide or sodium hydroxide. And those are aqueous compounds. They love to dissolve in water. And so the number one purpose for our solvent in this reaction, plus in the reaction that we did in lab 6, even though these are SN2 reactions, we needed a protic polar water solvent to dissolve our salts to make sure that we got a good nucleophile floating around as a charged species. Okay? A very fast overview of lectures 16 through 18. So please feel free to go back and look at those notes. Okay? The very last lecture, 18, we left with this clicker question. No more clicker questions. But what I'll try to do at the end of every lecture is I'll continue to post these clicker questions, and then they'll be there for us to ask questions about during our Zoom class meetings or Zoom meetings where you can ask me questions about the answers to these. This one was interesting, though. I wanted to come back to it because we have a lot of information on here, and which one A was the winner, but why did I write no reaction on some of these? And this one should also, have been no reaction as well. Why are these no reactions? And what I want to be very clear about is they're not just no reactions. There, no SN2 reaction takes place. No SN2 reaction takes place. It doesn't mean they can't react some other way. Maybe we'll see something soon. Hint, hint, nudge, nudge, wink, wink. That'll make them react. But under SN2 conditions, these do not react. So let's be really clear about this. The reason they don't react is because in this no SN2 reaction, this was a very poor nucleophile. So that is what stopped that reaction from working. In the second no SN2 reaction, it was the bulkiness of this substrate that caused it not to work. And so even though I have a great nucleophile, there's no way I can have an SN2 reaction on a tertiary aliphatic carbon. And the other no SN2 reaction, again, was due to this poor nucleophile, that it is uncharged and can't actually do a backside attack, even though I have a primary benzylic carbon, which is great, and an aprotic solvent, which is great. You throw a poor nucleophile in, and this is not going to react at all. No way. Okay? By the way, you like my ocean? We're trying to be positive here. I'm on the beach in Orgoland in cyberspace. I can be anywhere. That'll be kind of fun. So, to summarize about SN2 reactions, let's not get wrapped up in the mechanism too much. It is an important mechanism. But keep in mind, these nucleophilic substitution reactions are a way for us to change the substrate leaving group and put on a new group, a new functional group. Making functional groups is what it's all about in Orgoland. How many different functional groups can you make? We can make these alkyl halides. We can make these alcohols, ethers. These are really popular. Nitriles, esters. These are things we're going to see a lot of. And this might be a really good slide to have on your 1 page of notes. Oh yeah, you won't need a 1 page of notes anymore. All the exams are now open notes. Wow. Okay. We'll come back to that. I'm sure you'll have questions about that. All right. So here's a question to answer just to see if you got it all straight. It's really kind of cool. This drug, AZT, has been known as an anti-HIV drug. And really, actually, this is the actual molecule of AZT. You can see this is a precursor on its way to the synthesis of AZT. But in this precursor, this is an SN2 reaction. And what I'd be curious to know, if you can find it, is to actually see if you can label all 4 parts to this SN2 reaction. And we'll start with leaving groups next time. And can you draw the structure of whatever the leaving group product is? What do I make over here? What has fallen off? Okay? Because that leaving group is completely weird and new. We've never seen it before. But guess what? Lecture 19B, we're going to see it again. And just to let you know, every slide I have now has a slide number on it. So this is slide 5. And so in our class meetings, if you have a question about this one, you can just say, hey, Nick, lecture 19.5, slide 5. What was going on with that AZT leaving group? Can you go over that? That'll make it easier for us to find when we're actually playing with it and asking questions about it. Okay? I hope you enjoyed your very first Orgoland in cyberspace. And I'll see you again soon. Bye.